Hi, everyone. Welcome back. This is the last chapter of Chemistry 101, Chapter 10. In this chapter, we're going to study three very unique types of compounds called acids, bases, and salts. Of course, they are kind of related, and there's a lot of concepts, some new concepts involved in this chapter. And I hope you pay very special attention to these concepts. As it turned out, Chapter 10, in my experience, is the most hard to understand chapter, and students normally get confused with these concepts. All right, as usual, this page shows you the general guidelines for this chapter. Like I said, we're going to talk about the acid and base theories, what they are, what acid and what are bases, and also even what are salts. And we're going to talk about the properties of an acid and bases, and also the reaction between acid and bases called neutralization reaction. And then we're going to talk about some calculations in acid or basic solutions, and also introduce the concept of pH. And finally, we're going to talk more about salts, okay, the product between an acid and base reaction. So basically, that's the general guidelines of this chapter: the theory of acid and bases, the concept of pH, and also some property of the salts. All right, so let's get started. Okay, first, there are two acid and base theories, mainly in general chemistry. Okay, in organic, we have another theory, but in general, we have two very commonly used acid and base theories. The first theory is called Arrhenius theory. In this theory, acid is defined as a hydrogen-containing compound. So you can see there are few terms when we define acid. First, this compound needs to have hydrogen, and then this hydrogen-containing compound will produce a species called hydrogen plus ion, and we also call that hydrogen plus ion a proton in aqueous solution, means in water. So in other words, acids, Arrhenius acid, are hydrogen-containing compounds that can give hydrogen plus when dissolved in water. Okay, such as this HCl, hydrochloric acid. Okay, I mean, HCl is actually a gas called hydrogen chloride, but when hydrogen chloride dissolves in water, the bond between an H and Cl will break. But when the bond break, instead of generating two atoms, we're generating two ions, the hydrogen plus ion and also the chloride ion. And because of this fact, hydrogen chloride dissolved in water is defined as an acid. We call the acid hydrochloric acid. So that's the basic definition of an acid: contains hydrogen, and also when dissolved in water can give a proton. Now, one extra word about why hydrogen plus ion are called protons. Okay, if you think about hydrogen, which is the first element in our periodic table, it has one proton because the atomic number is number 1. So one proton hydrogen atoms, when they lose the owning electron, because one proton only has one electron, when they lose the owning electron, so what's left behind are basically a proton. So basically, hydrogen plus are alternatively called a proton. Of course, we know hydrogen comes with isotopes, but majority of hydrogen are hydrogen 1, which doesn't have any neutrons. So usually we call hydrogen plus protons. Okay, again, Arrhenius acids are hydrogen-containing compounds that can produce hydrogen plus, and of course the negative ion in water in a solution. Now, very similar Arrhenius base. Okay, Arrhenius base are hydroxide-containing compound. Okay, if you forgot from chapter 4 and 5, we have polyatomic ion. Hydroxide is OH. So Arrhenius base are OH containing compound. Okay, sodium hydroxide, lithium hydroxide, potassium hydroxide, etc. These hydroxide containing compounds will produce hydroxide ions, okay, OH minus ions, when dissolved in water in solution. Okay, such as sodium hydroxide. This is an ionic compound. We know in chapter 4, sodium hydroxide is an ionic compound containing polyatomic ion hydroxide. When it dissolves in water, it will produce sodium plus ion and hydroxide ion. And because of that, sodium hydroxide is defined as a base. It's defined as a base. Now, depending, the two processes we have just talked about, the acid gives hydrogen plus, the base gives OH minus. These two processes, they both produce ions, but these two processes actually happen in different fashion or different ways. When acid, such as hydrogen chloride, HA, okay, we're using like a generic formula, HA, dissolves in water. Because HA is a covalent compound, it doesn't even have ions in the structure. HA are actually bounded with covalent bond. You can see this is the structure of an HA. The bonding between H and A is a covalent bond. So we know HA doesn't even have ions, but it actually, when dissolved in water, the HA bond breaks, produces ion. So we call this process of from no ions to producing ions, we call the process ionization. Okay, ionization, because HA doesn't have any ions initially present in their structure. It's a molecular compound, it's a molecule HA, in fact. Now, on the other hand, for base, for areneous base, like sodium hydroxide, potassium hydroxide, MOH, we use that MOH as a generic formula. We know these are already ionic compound. So their structures already have ions present. Okay, M plus ion, sodium plus ion, or OH minus ion, right? They are ionic compounds. So when dissolved in water, what happened is these ions simply separate. Of course, with the help of water, it will help breaking down the crystal lattice. So this process is called dissociation because the ions are already present. What happened is the ion breaking apart become free. So these two processes, the name of these two processes, or you know what happened, are slightly different. Okay, acid, the process is called ionization, producing ions. Bases, dissociation, the ions basically separate by water. Okay, by water. All right, again, the definition of acid is producing a proton. The definition of base is producing, the definition of acid is producing proton. The definition of base is protein OH minus hydroxide ion. Okay, that's the definition of areneous base and acid. Now, this theory is very useful. It can help us to define many acids and bases, but there are some limitations or problems of this theory. One thing is, remember this theory, no matter defining acid or bases, we're talking about the acid bases dissolved in water. Okay, dissolved in water. But some compounds, their behavior are already acidic or basic, or their behavior are already acid or bases, even in a non-aqueous solution. That means even when they're not dissolved in water, they can still behave acid and base behaviors or properties. Okay, properties. Or this theory, the areneous theory, cannot explain compound like NH3, which doesn't have hydroxide, right? We know bases are hydroxide containing compound. NH3 is actually a base, but it doesn't have any hydroxide ion in the structure. But when you dissolve NH3 in water, it will produce a basic solution, basically. So again, areneous theory is very useful, but it has the problem of not being able to explain acid and bases when they're not dissolved in water, or some compounds in gaseous state. Okay, they can still behaving as acid or base. So these are the limitations of areneous theory. And because of that, we here introduce a broader acid and base theory called Bronsted-Lowry acid and base theory. In this theory, the concept is broader. An acid is simply defined as a donor of a proton or donor of protons. Okay, any substance, doesn't matter what substance, it doesn't matter if it dissolves in water or not, as long as it can donate a proton. Again, proton is hydrogen plus. Okay, donate. So two very key words for Bronsted theory of acid and base. Donate a proton. Proton donor. If a substance can donate a proton, then the substance is called an acid. Of course, Bronsted base theory is very related to the Bronsted acid theory. That is, a substance, in order to be a base, it must be able to accept a proton. Okay, we call proton acceptors are bases. See, this theory basically is focusing on what? On the proton. Acid donates proton. Base accepts proton. Okay, accepts proton. One is proton donor, one is proton acceptor. Later on, you actually see that this theory is all about the transfer of proton. One guy, the acid donates, the other guy accepts. So it's basically the transfer of proton. That's the essence of Bronsted-Lowry acid and base theory. Okay, let's take a look at the following two examples. Okay, two examples. The first equation shows what happened when HCl dissolves in water. HCl donates a proton to water. So water becomes H3O plus. Okay, because the water HCl donates a proton. And of course, HCl donates a proton, HCl becomes what? Cl minus. And then water accepts that proton. And when water accepts the proton, water becomes H3O plus. So what happened is the proton is basically transferred from HCl to water. Okay, from HCl to water. Let me erase it. Proton is transferred from HCl to water. Transfer means HCl donates, water accepts. So HCl is the acid, water is the base in the first equation. The second equation, you can see that is kind of opposite. Instead of water accepts the proton, in this case, actually water donates a proton to what? To NH3. When water donates a proton, water becomes what? OH minus. When NH3 accepts proton, NH3 becomes NH4 plus. You see that? So in this case, water serves as a proton donor. So of course, in this case, water is the acid, NH3 is the base. Whoever donates the proton is the acid. Whoever accepts the proton is the base. Okay, that's Bronsted-Lowry acid and base theory. Now, of course, you might wonder what's going on when water takes a proton. Why protons are accepted by water? Okay, in aqueous solution, that means when water is a solvent, proton, because it's a highly charged species, okay, very highly charged because it's a small and highly +1 charge, it cannot exist in the free state. It will always bond to water molecules to form a more stable species called hydronium ion, H3O plus, okay, called hydronium ion, H3O plus. What happened is the lone pair of water accepts the proton and makes a bond with that hydrogen because the hydrogen proton is empty, right? Proton has no electrons. So the lone pair of the oxygen of the water make a bond with the hydrogen. And we know this bond is called a coordinated covalent bond because both electrons between that OH bond came from oxygen. The hydrogen doesn't even provide electron to share. The shared pair after the bond is made, both from the oxygen. Okay, both from an oxygen. And that's an example of another example of of coordinated covalent bond. Okay, we talk about that in chapter 5. You can pause it and go to chapter 5 notes to take a look. Okay, anyway, what happened here is again, water accepts the proton to become hydronium ion. Okay, to become a hydronium ion. And that's basically how proton exists in water in reality. Okay, we know sometimes we show proton H plus, but in reality, proton is hydronium ion, H3O plus, if water is the solvent. In most cases, water is the solvent for acid-base reaction. So that means in water, you don't see any free protons. You only see H3O+, the hydronium ion. Okay, hydronium ion. So here is a generalized reaction showing Bronsted-Lowry acid and base theory. The acid contains hydrogen, will donate a proton, hydrogen plus, to the base. So the acid HA will become, acid HA will become, donates a proton to the base. Acid HA will become A minus, and the base accepts a proton, base will become BH plus. So now you can see that where the proton is located. The proton is located, transferred from the acid to what? To the base, okay, to the acid base. And also it tells us, in order for a substance to act as a proton donor, you must have another substance to behave as a proton acceptor. The process of donating and accepting proton must happen simultaneously. It means happen at the same time. There's no individual process. That's what we call Bronsted-Lowry generalization or transfer of the base, as the theory of acid and bases is the transfer of protons. Okay, transfer proton. And this is again the generalized reaction showing an acid and base reaction. Very important. Okay, you understand the species that donates the proton, and also the species accepting the proton, and also after donating and accepting what the species, what both acid and base become. Acid becomes A minus, base becomes BH plus. Now, based on the generalized equation, if you remember, we talked about in chapter 9, all reactions are reversible. Technically speaking, are reversible. So if after the acid and base transfer, if the products A minus and BH plus can reverse back to the original acid and base. Okay, if the reaction is indeed reversible. Some reactions we didn't write as reversible because some reaction goes to completion. We assume it is not reversible, but all reactions again are technically reversible. So if an acid and base after the transfer proton, the products can go back to the reactant, and you will notice that the proton will be transferred in a reversed way, right? Remember, before that is the transfer of proton from acid to base. And then if the reaction is reversible, then the proton will need to be transferred from what? From the BH plus to A minus. Okay, you need to transfer it back. That's the reverse reaction. But if you remember the definition of acid and base, if this guy HB plus can transfer a proton, can give a proton back to the A minus, then BH plus can also be called an acid, right? Because it has a proton to donate. A minus, because it can take a proton back. So because if it can accept a proton, A minus can also be called a base. You see that? We start with an acid and a base, we end up with acid and base. We always are getting a pair. Now let's take a look at the names of these acid and base. I'll erase more. In this generalized reaction, the forward reaction again is the acid transfer the proton to the base. Okay, transfer the proton to the base. That's no problem. The acid transfer proton to the base. Acid proton donor, base proton acceptor. But after the acid transfer the proton to the base, the acid becomes A minus. We call that the conjugate base of the acid. The conjugate base of the acid. It becomes the base after transfer the proton. Why it becomes base? Because A minus here can now accept a proton because the proton is going away. Now it can accept a proton back. So the acid now becomes a base. We call that the conjugate base of the acid. Very similar. When the base accepts a proton, now base has a proton now after accepting it. So the BH plus is called an acid because it has a proton on it. And that acid is called the conjugate acid of the base. See that acid becomes conjugate base. Base becomes conjugate acid. Okay, we're always getting a pair of this acid and base. Take care of the acid base. Acid. Okay, now let's erase. Acid becomes base. The difference between acid and the conjugate base is what? Is a proton. Base become acid. Of course, base become conjugate acid. The difference between these two is also a what? Is a proton. Okay, is a proton. So you can see that is always based on what? Proton. The acid, take away the proton, becomes the conjugate base. The base gets a proton, become the conjugate acid. Okay, let's take a look at a real example. Okay, on the left side, we have acetic acid, ACOH. This is where the proton is going to be donated. After ACOH donates a proton to water, okay, to water, the ACOH becomes ACO minus, and we call that the conjugate base of the acid. And we know the water is the one accepting the proton, so water is the base. And after water accepts the proton, water becomes H3O plus. Water becomes the conjugate acid of the base. Okay, acid of the base. So how do we get a conjugate base? We remove a proton from an acid, we get the conjugate base. How do we get a conjugate acid? We add a proton to the base, we get a conjugate acid of the base. The difference between acid, conjugate base, conjugate acid pair is owning a proton. Base has one less proton than acid. You can always refute that. Okay, base has one less proton than an acid. Acid is a proton donor. Base needs to accept it. That's why base always has one less proton than the acid. Okay, let's take a look at this example. See if you can identify the species. This reaction is something we have seen before. Is water donates a proton to NH3. So water is the acid, NH3 is the base. Okay, I use A and B stands for acid and base. But after water donates a proton, water becomes OH minus. We call this conjugate base of the acid. And after the base accepts a proton, the base becomes conjugate acid of the base. Okay, let me rewrite. It's a little weird. This is acid. That's base. This is the conjugate base of the acid because you donate a proton. This is the conjugate acid of the base because you get a proton. Okay, gets a proton. So again, acid acid HA donates a proton, becomes A minus, acid conjugate base. Base gets a proton, becomes the conjugate acid, BH plus. Okay, always practice. Okay, practice with that. NH3 gets a proton, become NH4 plus, right? B becomes BH minus plus. Okay, always practice the acid and base pairs. Okay, that's very important for understanding the transfer of electrons. Okay, here, one more practice. Identify the conjugate acid pair in the following equation. Okay, we know the equation has HF and water. Okay, HF and water. HF is the acid, donates a proton, becomes F minus. So HF and F minus is a conjugate acid and base pair. Okay, that's a conjugate acid and base pair. So A, answer is B. Okay, another pair, of course, is with water and hydronium ion. They're a conjugate base and acid pair. Okay, conjugate acid and base pair, and base and acid pair. So HF, remove a proton. Okay, HA, see that? Remove a proton becomes A minus. Okay, that's the conjugate acid and base pair. Okay, answer is B. Now, another look of these two equations. We have seen this equation quite a few times already. Both equations involve water. The first equation, water is the proton acceptor, right? Proton donates from HCl to water. Proton acceptor, we know proton acceptor is the base. The second equation is the water donates a proton to NH3. So in this case, water is the acid. Okay, first equation, water accepts a proton. Second equation, water donates a proton. So water, this compound, this molecule, can either lose or accept a proton, right? Can donate and accept a proton. That means water can either act as an acid or a base. Species like this, we call amphoteric substance. Okay, amphoteric means what? You can both serve as an acid and base, depends on what the other substance is. Okay, when another substance is an acid, water serves as the base. When the other substance is a base, water serves as acid. Substance like water, again, is amphoteric. Okay, one extra word, if you notice that, what makes a substance amphoteric? It has a proton. First has a hydrogen that can donate as a proton. That's number one. And also it has a lone pair that can accept a proton. Remember, water accepts a proton becomes hydronium. And water making a bond with the proton using the lone pair on the oxygen. So in order for a substance to serve as an amphoteric substance, it both must satisfy these two conditions. One is with a hydrogen that can ionize or donate as a proton. Number two is has a non-metal atom or metal atom, mostly non-metal atom, has a lone pair of electrons that can accept a proton. Okay, accept a proton. Now, when we talk about acid, okay, talk about an acid, are substances that contains hydrogen that can dissociate, or I'm sorry, that can ionize to give protons. Some acids, okay, some acids may have more than one hydrogen that are potentially ionizable. Means can ionize to produce more than one hydrogen when you have a base around. And those acids are called polyprotic acid. Polyprotic means what? It can produce more than one proton per molecule. Okay, here are three examples demonstrating this very simple and easy concept. The first acid is the one we have seen already, with only one hydrogen ionizable, so it will donate one proton per molecule. Hydrochloric acid, we call that monoprotic. Okay, but acid like sulfuric acid, H2SO4, you can see there's two hydrogen. In fact, both hydrogen in H2SO4 can potentially ionize to produce two protons per molecule, potentially. Okay, later on, we can talk more about it. And if that's the case, sulfuric acid is a polyprotic acid because there's two protons, we call it diprotic acid. Okay, another example is phosphoric acid, H3PO4. You can see it has three hydrogens. And again, potentially, those three hydrogens can ionize to produce three protons per molecule, even though the process is very weak. Okay, all protons ionize, but potentially they can ionize all three to produce protons. And H3PO4 phosphoric acid is also a polyprotic acid because it has three protons. We call it a triprotic acid. Okay, triprotic acid. So that's the definition of these polyprotic acid. Just in case you see these acid, you know, they may potentially produce more than one protons. But one thing I do want to point out, we know acids are hydrogen-containing compounds that can ionize to produce protons. But if a molecule contains hydrogen It doesn't mean all the hydrogens in the formula or in the structure can produce or can ionize into protons. Okay, you have to analyze case by case. Of course, you will learn more once you study the chemistry, the structure of the acids. We don't elaborate too much here, but I want to just show you when you have a molecule contains multiple hydrogens, it doesn't mean all hydrogens will be ionizable. Okay, the previous three examples, all these hydrogens are ionizable, but not all the cases. For example, this is the structure or the formula of acetic acid. Acetic acid is 4 hydrogens, but in fact, only the hydrogens bonded to the oxygen, that hydrogen is ionizable. The other 3 hydrogens bonded with carbon that are not. Okay, are not. So acid like this is still monoproduct because acetic acid only has 1 ionizable hydrogen to become proton. The other 3 are not. Okay, now so you cannot classify all acid that has multiple hydrogen as polyproduct. It has to be case by case. Okay, usually like organic acid, like these hydrogen bonded to carbons won't be ionizable. Hydrogen bonded to nitrogen, mostly oxygen, will most likely to be ionizable. Okay, just again, we don't elaborate here, but there are many hydrogen containing compounds and may not even be acid. Okay, it depends case by case. All right, next concept. Okay, like I said, this chapter, we do have a lot of these small concepts and something are very new. So I want you to, again, you can always pause the video and to digest and look back and before moving on, okay, before moving on, that you don't have to follow this pace of this video. I hope you do understand all these little concepts. Okay, next, let's talk about the strength of acid and bases. First, the strength of acids. Okay, we know acids are proton donors. Okay, after donated, a proton acid becomes what? The conjugate base. HA becomes A minus after donating a proton. Now, if an acid completely ionized, that means all the HA becomes A minus. There's no HA left after donating the proton. Okay, completely ionized. All HA becomes A minus, of course, become proton. Proton is accepted by water in this case. So you can see all HA all become what? A minus and hydronium ion. If that's the case, if the ionization is complete 100%, transfer of electron from acid to water, if that's the case, we call the acid a strong acid. Strong because completely ionized. And strong acid, the equation, we use a single arrow. We assume the reaction is not even reversible because again, the transfer of electron is complete, okay, almost 100%. Now, most acids, okay, the reason I say most acid, we'll show you next slide. Most acid HA, when they ionize, as you can see this bar chart, most of the acid remain intact. Only a small percentage of the acid, in fact, ionize. That's the case for most acids. Only a small percentage of the acid molecule HA ionized become A minus and of course hydronium ion. And those acids in the equation we use double arrow because the reaction again is reversible. And in fact, the reversible reaction favors the reactant because only a tiny percentage become what? Become these two, ionized. And we call those acids weak acids. Like I said, most acids are weak acids. Okay, but you need to know the difference between strong and weak and how do we represent those? Strong acids, 100% completely ionized, no HA left. Weak acid, owning a tiny percent, 5%, less than 5%, 2%, 1%, ionized become A minus. Majority of the acid remain intact as HA, and those are weak acid. Strong acid, we use single arrow, and weak acid, we use double equilibrium arrow. Okay, the reason I said most acids are weak acid is in nature. We only have 7 common strong acids. There are other strong acids, but these are the most commonly seen strong acids. Some even books say 6 or 7. Here, our book listed 7, so we memorize those 7. Your lab may list it 6. I'm not 100% sure, but again, between 6 and 7 commonly strong acids. Okay, they are hydrochloric acid, hydrobromic acid, hydroiodic acid, nitric acid, perchloric acid, and sulfuric acid. Okay, the only thing that's maybe have an ambiguity is the chloric acid. Okay, maybe your lab doesn't list this one, your book listed. Again, 6 or 7 strong acid. The other 6 are definitely, in common sense, are the strong acids. Again, those acids means what? When they ionize to produce proton, they ionize completely. There's no acid molecules left in the solution. Hydrochloric, hydrobromic, hydroiodic, nitric acid, perchloric acid, HClO4, perchloric acid, and H2SO4. And chloric acid, again, is listed in this book, then we assume that's a strong acid too. Okay, among these 7 strong acids, okay, if you want to know, perchloric acid is the strongest among those 7. It's the strongest acid among those 7. Very similar definition about strong versus weak. We have that on bases as well. We know bases are mostly what? Hydroxides. Okay, hydroxides based on Arrhenius definition. Most are hydroxides. So metal hydroxides, especially group 1A alkali metal or group 2A alkaline earth metal, the hydroxides of these 2 group metals are strong bases. Okay, strong bases. And those strong bases means they will dissociate completely in water. Okay, but pay attention to group 2A metals. Okay, we don't include beryllium hydroxide or magnesium hydroxide. We assume these 2 hydroxides are weak bases. But starting calcium, strontium, barium, these 3 bases are strong bases. The group 1A metal hydroxides are all strong bases. Okay, again, strong bases are mainly hydroxides of group 1A and group 2A metals. And if you remember chapter 1 and 2 and also our lab, these 2 metals, we even give their names, and their names have the word of base. Alkaline metal, alkaline means base. Alkaline earth metal, okay, alkaline means base. Okay, but again, group 2A start with calcium. Okay, start with calcium. So these are the strong bases that completely dissociate to produce hydroxides. In contrast, weak bases usually don't contain hydroxide. Weak bases are usually ammonia, like NH3, or organic derivatives of ammonia. We call them amines. Okay, of course, in this class, we're not going to study organic molecules, but I want to give you the inorganic molecule ammonia as an example for weak base. Okay, and again, we have seen this reaction before. Ammonia, the reason it can serve as a base because water can donate, let me erase that, water can donate a proton to ammonia. And because ammonia can accept a proton, ammonia is a base. But the reaction, you can see that the arrow. Double arrow favors what? Favors the reactant, means the production of this hydroxide is very minor. Okay, very small percentage of the transfer electron happened in solution. That's why ammonia is a weak base. Okay, most molecules remain intact as NH3 and water. Only a small percentage produce these 2 ions, produce the conjugate acid and the base, of course. And because of that, ammonia is defined as a weak base. Okay, as a weak base. So that's the information about the strength of acid and base. Okay, strong means complete. No matter ionization for acid or dissociation for base, complete means you don't have intact molecules or compound left. Weak means what? A small percentage, either ionized or here transfer of proton. Now, because most acids are weak acids, like we said, we only have 6 or 7 strong acids. So we must have a way to quantify. Okay, we have a way to quantify the strength of acid, or of course, the strength of bases as well. Okay, strength of acid or strength of bases as well. And the way to quantify the weak acid or weak base is through something we talked about in chapter 9, through equilibrium. Okay, through equilibrium. If you remember, when an acid or base are weak, we use what? We use equilibrium, double arrow. So weak acid or weak base reactions are basically chemical equilibrium. And if we have an equilibrium, we can define the equilibrium. We can describe the equilibrium using a constant we talked about in chapter 9 called equilibrium constant, K. Okay, again, if you forgot about that, go back to the last part of chapter 9 when we talk about chemical equilibrium and what is equilibrium constant K. Now, let's take a look at this weak acid equation. Okay, again, a weak acid, HA, donates a proton, becomes A minus. Water accepts a proton, becomes hydronium. And we use what? We use double arrow to represent the equilibrium. So that's a reaction of weak acid. Okay, HA, of course, the generic form of an acid, of a weak acid. Now, since this is equilibrium, we can write the equilibrium constant, product over reactant concentration. Okay, product concentration over reactant concentration powered by their coefficient. The coefficient is always 1, are all 1 in this case, so we don't have any exponent on these concentrations. So we have product concentration over reactant concentration. Someone will ask, hey, when you write equilibrium constant, concentration product over reactant, why don't you include water? Okay, again, pause the video, go back to chapter 9, you will find out when we have equilibrium constant expression, we do not include pure liquid or solid. Okay, water is a pure liquid, right? Water is a liquid, pure. So the concentration of water is 1. That's why we don't include the concentration of water. So we only include the concentration of the products, the conjugate acid base over the reactant, of course, the acid. Okay, powered by the coefficient. Of course, coefficients are always 1. Not always, are all 1 in this case. Okay, always in 1 case. And the K, we put a subscript A to tell people this Ka stands for acid. We call that acid ionization constant. It is an equilibrium constant, but we call it acid ionization constant. Okay, again, take a look at the equation, what the equation means. We have seen this equation many times. And how do we write the Ka for an acid? Product over reactant powered by the coefficient, do not include water. Now, if you take a look at this equation, this K, you will find out if you have more products, okay, if you have more products, then K will be what? K will be bigger. If K will be bigger means more products mean what? The reaction moves more forward because more product, more ionization. So in another word, okay, in a summary word, greater K means more product concentration, means more acid ionized, means the acid is stronger. Or opposite, reversely, acid, when acid is stronger acid, the Ka will be bigger, will increase. So we can use the ionization constant of an acid to describe the relative strength of it. We know most acids are weak, but even they're all weak, they have still different strength. Some are stronger, some are weaker, even they're all weak acids. Stronger ones with greater Ka, weaker ones with smaller Ka. So here you can see in this table, Okay, not a complete table, but the table lists the sum of the weak acids. Okay, a few weak acids, and the Ka is listed as well. Okay, you can see the Ka is what? It's a relatively small number. 10 to minus 3, 10 to minus 4, 10 to minus 10, 10 to minus 13. It's very, very small numbers. But you can see that higher Ka means the acid here around on the top are stronger. Smaller Ka, the acid are weaker, very weak. And you can also see that the percent of ionization, right? Higher percent means more ionization is stronger. These acids are relatively stronger, so the percent of ionization is not bad, 10%, 8%, 2%, right? It's one per, still some percent. But if you can see this weak acids, the percent is what? Less than 1%, much less than 1% means what? The acid barely ionized. Okay, it's like a 1 per 1,000, 1 per 10,000, like that's that range. That means what? Means the acid barely ionized. Most of the molecule remains intact. Okay, so Ka is a very good ruler to measure the strength of an acid. Higher Ka, equilibrium favors to the right, move forward, because more product, the acid is stronger. Stronger acid means greater percent of ionization. Okay, greater percent of ionization. Now, after you understand Ka, let's take a look of a diprotic acid we have introduced before, sulfuric acid, to show you what happened when an acid contains more than one ionizable proton. We know sulfuric acid has 2 hydrogens. Okay, both hydrogens are ionizable. That's why sulfuric acid is called a diprotic acid. Okay, but both hydrogen, I always use that word, potentially ionizable, because the fact shown here. These 2 protons are not ionized the same time. They're actually ionized in successive steps, one after another. And you can see that each step has its own Ka. The first proton, donate to water, of course. The acid becomes the conjugate base of this acid. The Ka is fairly big. The Ka is 1,000. 1,000 Ka means what? 1,000 over 1 means 1,000 product over 1 reactant. Means what? The reaction is very basically go completion. Okay, but you can see that the first step, we even use single arrow. That is the strong acid of sulfuric acid. We define sulfuric acid as a strong acid. This is the stronger proton, the stronger hydrogen, the first step. But if you take a look, after the first step, we got this guy. Okay, 1 proton left with a negative charge. And then this guy can still donate another proton to water. But now, the second step, the Ka is what? 1 times 10 to the negative 2. Means what? Much smaller. The first one is 1,000, 10 to the third. The second one is 10 to the negative 2. It's much smaller. Means what? Means the second proton is almost a weak acid. Okay, almost weak acid. If you look at the chart, when it was 10 to negative 3, the percent is 8%. Okay, 10 to negative 2 is no longer 100%. Why is that? Okay, why is that? Because the second proton is donated from a charged species, if you look at it. Right? The second proton came from what? The second proton came from this guy. This guy is negatively charged. Taking a proton from a negatively charged species, proton is positively charged. Taking a proton from a negatively charged species is much more difficult than taking a proton from a neutral molecule, H2SO4. That is why, the main reason, more straightforward reason, explanation, that is why the second proton ionized is very weak. Okay, relatively very weak compared to the first one. Okay, compared to the first one. And also, again, demonstrated here, if you have a polyprotic acid, the protons are ionized in successive steps. The first K constant is much greater than the second step. If the third proton, then the third proton K is much smaller. Ka1 much bigger than Ka2, Ka2 much bigger than Ka3. The reason is harder and harder to remove a proton from a negatively charged species. Okay, negative charged species. But again, it also showed K, the equilibrium constant, is a very good ruler to what? To measure the strength of acid, even within the same acid. Okay, within the same acid. Now, very similar. Here is the equation for a base, a weak base. Of course, we know weak base is accepting a proton from water. Okay, accepting a proton from water. So B becomes ZH plus water becomes OH minus. Okay, and very similar. For a weak base, we can write a equilibrium constant, Kb. Okay, acid is Ka, base is Kb. We call that base ionization constant. Of course, the same product concentration over reactant do not include water. So product over reactant, you can see that concentration, the bracket stands for concentration without including water. Okay, that's the expression for Kb. Okay, the same, higher Kb, the reaction has more product. That means the ionization is moving more forward, means the base is stronger. Okay, lower Kb, the base is weaker. Okay, Kb can also be used to measure the strength of bases. Now, after we introduce acid and base, let's take a look at the reaction between an acid and base. Okay, the reaction between an acid and a base. When an acid and a hydroxide base, okay, like potassium hydroxide, sodium hydroxide base, react. Okay, here is one of the example. An acid, HCl, a base, KOH, react. The proton from the acid will react with the hydroxide of the base to produce HOH, H2O, basically water, and an ionic compound. Okay, ionic compound. We call this reaction neutralization reaction. This neutralization reaction can very easily be understood as a double replacement reaction. If you remember double replacement, if you forget about double replacement, go to the first part of chapter 9 and take a look. Double replacement means what? You're swapping the partners, the ions. Okay, H combined with OH, K combined with Cl. H and OH becomes water, K and Cl becomes KCl, an ionic compound. We call that a salt. We'll talk more about the salt later. Of course, another way of understanding this reaction is the acid donates a proton to the base to give water. And of course, what's left behind are the Cl minus from the acid and K plus from the base. You got a KCl. Okay, there are two ways of understanding this reaction. But one thing you need to be making sure, that is, no matter what acid and base are reacting between, the amount of the proton from the acid must equal to the amount of the hydroxide from the base. The amount must be equal to neutralize. Okay, here in the first case, of course, HCl only has one proton, KOH only has one OH minus, so they react with 1-to-1 ratio. But if you take a look at the bottom case, sulfuric acid has two ionizable protons, means sulfuric acid can produce two protons. So if you use KOH, that means what? You need to balance the equation by adding a 2 in front of KOH, because you need to supply 2 OH minus to neutralize the 2 protons from sulfuric acid. Of course, you get 2 water, right? 2 hydrogen and 2 OH, you get 2 water. And of course, the other product is ionic compound, K2HO4, SO4. Okay, that's the formula of potassium sulfate. And also you can write the formula of ionic compound. We have learned how to write the formula of ionic compound in chapter 4 as well. The charge of sulfate is -2, remember? The charge of potassium is 1. So the charge of the sulfate becomes the subscript of potassium, which is 2. Okay, don't forget about that. Okay, but you have to balance the equation again by what? By providing equal amount of hydrogen plus and OH minus to react. And again, the product is water and an ionic compound called salt. Okay, called salt. Of course, we will talk about more salt in the final part of this chapter. Okay, but again, salts are compound containing a metal or ammonium as the positive ion and a non-metal or a positive ion as a negative ion. Okay, KCl, K2SO4, KNO3, sodium NO3, sodium chloride, sodium bromide. As long as you have a metal or ammonium as the positive ion, or a non-metal or a positive ion, polyatomic ion as the negative ion, you get an ionic compound, except hydroxide. Of course, hydroxide is base. So these compounds are all called salts. Okay, essentially, they are products from an acid and base reaction. Of course, one of the product, the other one is water. Okay, they are the products between an acid and base. Okay, the ions are actually from an acid and a base. K from a base, Cl from an acid. Here at the bottom, K is from the base, sulfate is from the acid. So basically, a salt is a product between an acid and base reaction. Okay, they are ionic compounds. Okay, they're ionic compounds. Again, we'll talk about more of salts in the later part of this chapter, but keep in mind, salts are ionic compounds. Okay, they are containing positive ions and negative ions, and these ions are essentially or actually from an acid and a base. Okay, an acid and a base. But again, make sure you are able to write a neutralization reaction between acid and base and considering the equal amount of proton and hydroxide. If not, you need to balance the equation and write the correct formula. Okay, write the correct formula. Now, because the acid and base reaction, okay, because the acid and base reaction, you have to satisfy the fact of equal amount of hydrogen and OH. Okay, they must be equal. So you can determine the ratio of the acid and base in the equation. Okay, here, for example, the ratio has to be 1 and 1, means 1 HCl react with 1 QH. 1 mole of HCl react with 1 mole of QH, because neutralization reaction, because the fact how they react. So because we know the ratio, okay, because we know ratio, we can use this fact to determine the concentration of an acid or a base if we know the concentration of another. Okay, for example, this exercise, okay, exercise, if you have 25 ml of the acid, and this much of acid can react with 14.8 ml of 0.351 molar of the base. So see that we know the molarity of the base, we know the concentration of the base, and we know the volume of each, how much we use to react. Then, if we know these data, we can calculate the concentration of this acid, which we don't know. And we call this technique titration. Okay, titration. What is titration? Titration is basically, okay, titration basically a neutralization reaction. You know how these acid and base can react. Then you use a measured volume of an acid or a base, and you know the concentration of it to determine the concentration of the unknown acid or base. Of course, you know the volume of each. Okay, for example, this is the setup of titration. Okay, this is the set of the titration. You know the volume of the acid or base. Okay, you know the volume of the acid or base that are being titrated, that's what we're using for titration. You know the concentration of that acid or base. You calculate the concentration of the other. Okay, you know the volume of both. Okay, one volume is measured, another volume we read from this device called burette, and then you know the concentration of one and calculate the concentration of another. Okay, I don't elaborate too much here of this experiment. I hope you watch the videos in the note area. I provided 2 or 3 videos for you to watch to know this technique, and most importantly, how do we use this technique to determine accurately the concentration of an acid or base using a known acid or base. Okay, using a known concentration acid or base. And of course, this is the exercise practice. Okay, I did not elaborate the exercise either because your web assignment has quite a few exercises explaining to you the principle of titration. How do we calculate based on the titration? And again, the titration is based on the reaction. It's called stoichiometry. So again, here for the technique of titration, make sure you watch the video. We have videos provided in the notes. And for the principle and calculation of the titration, make sure you complete and study your web assignment. Okay, there are videos involved, and also there are exercises and practice involved you can practice with. And of course, the key for this exercise is provided as well. You can do that afterwards and see if you understand this technique. Now, when we do titration, okay, one extra word about titration is we need to know, okay, we need to know when the acid and base react in equal amount, right? We need to know what is the end point of the titration, because you're keeping adding things from this burette to the beaker, right? You keep adding drops into the beaker. So you need to know when to stop, that you know the acid and base are reacting in equal amount. Okay, we need to know that visually, and that is determined by the color change of the solution. In order to make the color change of the solution, we need a special compound called an acid-base indicator. The acid-base indicator normally is an organic compound, but it will change color when the pH changes, when the acidity or basicity of solution changes. That means when they're reacting with each other, the acidity of the basicity of the solution will change. And at that point, at the point of pH change you want it, you select a different indicator, so the color change will tell you the titration has reached to the end. Of course, different indicator changes different colors. You can see some change around a pH of 8, some change around a pH of 9, some change 10. Depends on the final point of the final product, the pH, you select different indicators. But you can see all these indicators, they change color from one to another, from orange to yellow, from colorless to orange, from colorless to pink, from colorless to blue to red. You can see the color change varies by a narrow range of pH. Again, they are selected based on the products of your reaction, based on what acid and base you're titrating with. But they all will change color and tell you at that point the acid and base has reached equal amount, so that you can stop, you can measure the volume and then calculate the concentration of acid or base. Okay, acid or base. All right, so that is all for the first part of this chapter. We talk about what are acid and bases, we talk about their properties, we talk about these very important concepts and theories of an acid and bases and the strength of them. And also we talk about the reaction between acid and bases. How do we understand the reaction, what the products are, and how do we, based on the reaction stoichiometry, to calculate the concentration of either an acid or base. Okay. Again, there are many small items, small concept. I hope you can watch the video a few times and make sure you understand these concepts. And in the second part, we're going to study the ionization of water. And from there, we can introduce you, how do we know the acidity or the basicity of a solution? Not only acid or base, any salt solution, we would need to know the basicity or acidity of it, and also, of course, the pH of these solutions, right? So I'm going to stop here and catch up in our part 2 of chapter 10. Bye now.